Yeah, so I'm John Kymissis, and I'm in electrical engineering at Columbia, and I'm very squarely an electrical engineer, and we'll talk more about that today. But before we start, I'm contractually obligated to advertise the university briefly, and many people don't know where Columbia is, and that's okay. We're located in Manhattan, in New York City. So this is the island of Manhattan, and most people, when they think of Manhattan, they think of maybe Times Square or Rockefeller Plaza. And Columbia actually used to be where Rockefeller Plaza now is. That land was actually eventually sold to the Rockefeller family. I mean, they first built Rockefeller Plaza, then they sold the land, which is weird, but that's like a New York thing. But that's all down here in Midtown. And we're located kind of in the boonies in an area called Morningside Heights. And we have, I mean, officially Columbia has 5 campuses, but you know, there's really the medical campus and our campus. And this is where I'm located. So it's a couple of blocks between 114th Street and 120th Street. And this is where my lab is and where our clean room is. And you know, and it's a nice place. We have 4 lawns exactly. So you can see there's some flags here. And the flags tell you if you're allowed to play Frisbee on the lawn. If the flag is red, you can only sunbathe or hang out. And if it's green, you can play soccer or Frisbee. Or people play this weird bouncy game a lot, which also requires a green flag. So we're located in this building, which even though it claims to have 10 stories, even though you only see like 6, and it's another New York thing. This level is well above the street level because of the way the campus is built. And most of electrical engineering is either in this building or the neighboring building. And you know, our department, it's pretty small. We have, as of last week, 30 faculty. Unfortunately, someone announced that he's moving. But we have about 100 undergraduates, and you know, we have a decent sized graduate program. But let me warmly encourage you to apply to our various openings. So for PhD students and postdocs, we have several open searches, including a robotics cluster search, which just means that you also have to convince the mechanical engineering department that you're the right person. But that has 3 lines in it, which is pretty nice. And then we also have an open search, which is in circuits. It's open rank, but it's not open topic. So it's in circuits and in signal processing. And so you can get links to those here. You can still apply, although we're a little on the late side. We haven't invited people for interviews yet. So if you have one more week, you know, have your advisor email us. And if you know any undergrads that are looking for a PhD program, of course, I should always encourage them to apply. And we also have links to our RU sites on our website for undergrads as well. So the vision of my group is to build and use thin film devices. And you know, many of you, I mean, Michigan has a lot of strength in this. If you work with Professor Forrest or Professor Kenneth or Professor Stein, you know what thin film devices are. But for most other people, it's a little bit mysterious. And I'm not going to talk about everything that I have here. I just grabbed some pictures from the lab. But you know, if you think back to your semiconductor course, you know, semiconductor course always starts at the mine, right? You dig silicon out of the ground, it's purified, and in the fires of Mordor, they draw this huge bowl of perfect single crystal silicon, all sorts of strategies for how to purify it and how to manage it. It's cut into plates, and then those plates are processed into wafers. And one of the things that's been amazing about this process is that the value multiplication that we have going from wafers that are unprocessed to wafers that are fully processed is just enormous. So a raw wafer is in the hundreds of dollars, whereas a finished wafer is in the hundreds of thousands of dollars. It could be even worth more depending on what's on it. If you're NVIDIA, you can probably make more than $1 million a wafer depending. And if this was not the CEO, he would have been fired for holding it with his bare hands. He was fired for other reasons, but that's another story. But you know, the thing though that makes normal electronics work, and this is about 80% of the value of the market, is the single crystal nature of silicon. With single crystal devices, what's great is when we build our transistors, we're able to inherit either directly or indirectly through epitaxy and other processes that nice, perfect crystalline structure with all the performance that comes with it. Now, in the thin film approach, many of the pioneers of whom are in this room, we do it differently. Instead of starting with the perfect single crystal, we start with the substrate and then we add other materials. And so in order to make that work, we have to be able to add materials that do something functional without that perfect single crystal underneath, and in many cases without that extremely high temperature that we are able to access when we draw our perfect single crystals from a melt. And so I'll talk more about this process in a minute, but basically we can start with the substrate and then sprinkle things on top. And that's why I, and Professor Peterson also, like to talk about electronics on anything, because we can start with something useful and we can make it even more useful. And then you can make it even more useful again, and you can stack things and have that kind of heterogeneous functionality and put it together that way. Now, there's a couple things that are good about it. I mean, what's nice is that we can reduce or eliminate the need for that templating, which you often need. And we can put electronics and everything, but it's not perfect. You know, the materials that are available for this type of thin film processing aren't going to be the same, and they're often not going to be as good as the materials you would start with in a single crystal. And what I'm hoping to convince you today is sometimes that's okay. And sometimes we can make things that still work and do something useful without having that single crystal magic that we're so used to in other electronic systems. And so I want you to think about this kind of like a box of puzzle pieces, and you can grab pieces of the puzzle and you can snap them together to make new things. Now, for me, the most important part of most of the devices we make are thin film transistors. You know, thin film transistors are transistor devices that we build without having to use that perfect crystalline substrate. And in particular, I've worked for a long time on organic field effect transistors. These are made using organic semiconductors, and I will be the first to tell you, despite my long, painful history with them, organic field effect transistors I don't think have any commercial applications. I think that ship has sailed. But at the university, they're pretty great because we can make them with almost zero capital investment, which is nice. But we can also make devices very, very close to room temperature. And this is because organic semiconductors are van der Waals bonded. So if you remember from chemistry class, van der Waals bonds are very weak bonds. And so to disrupt the van der Waals bonds and to let them reform doesn't require the input of a lot of energy. And so what we can do is we can start with material in a bottle and move it from the bottle to the substrate, get it off the substrate, without having to invest enormous amounts of energy and without making or breaking any covalent bonds, which then give you those pesky mid-gap states that damage performance. And so what we can do is we can start with the substrate with some material which we want to functionalize, and then at or very close to room temperature, we can sprinkle transistors on, add switching, add gain, and use that to make some new things. So what kind of new things? So one thing that I've been a little bit obsessed with is making touch sensors. And touch sensors can be useful in robotics. They can be useful for surgical systems. They can be useful in lots of areas, safety devices. And one way to do touch sensing is using piezoelectric materials. And in particular, I think piezoelectric polymers are especially strategic for touch sensors for a few reasons. Now, piezoelectric polymers have been known for some time. There's a little bit of a joke, a little bit like organic transistors, that PVDF, which is the champion piezoelectric polymer, is the material of the future. And it's been known since the 70s. But what's nice about PVDF is it's a very inexpensive polymer material, and it can be drawn in large sheets, and it can be crystallized into a phase in which every other carbon has either hydrogens or fluorines. And in one of its crystalline phases, you can set it up so that the fluorines preferentially point one way and the hydrogens preferentially point the other. And this creates an internal dipole because the fluorine's more electronegative than the carbon, and the hydrogen's actually a little bit electropositive relative to the carbon. And so that makes a dipole that allows you to then have the dipole inside that makes the material piezoelectric. And because the material is extremely soft, the transduction of force to strain is actually quite good. And so even though the D33, or the transduction of strain to charge, is not that great, it's only about 1/10 of what you have for a ceramic piezoelectric material, the transduction of force to charge, or G33, is actually excellent. It's one of the best that's known. So that low modulus is nice. A second advantage is that PVDF can also withstand a strain of 3%. And I challenge any ceramic to withstand a strain of greater than 1% without cracking. And so with PVDF, we can apply larger forces, we can have higher impulses, which is nice. And it also has a great acoustic impedance match to water. And so in addition to being a great microphone and touch sensor, it can also be a good hydrophone. And there's some interesting applications for that. So there's lots of nice things about it. I mean, why don't we use it for everything? And why do we always joke it's the material of the future? Well, it has a number of weaknesses. And one of the biggest weaknesses is that crystalline form I mentioned before, in which we stretch it and set it up so that the fluorines point one way and the hydrogens point the other. It turns out that that is not the thermodynamically stable phase of PVDF. Unfortunately, the thermodynamically stable phase is paraelectric, where the fluorines and the hydrogens are not preferentially oriented in one direction. And so PVDF, if it's heated, depending on how you crystallize it, to somewhere around 90 degrees, maybe 95 degrees, it unfortunately undergoes a solid phase recrystallization in which you lose its piezoelectric characters. That really limits the thermal budget with which we can process it. This is, incidentally, a lot like chocolate. We just did an event. I did a material science of chocolate thing earlier this week for Valentine's Day. And it turns out that the tempered phase of chocolate, which is the favorable phase, is also not the thermodynamically stable phase of chocolate, which is why when you get chocolate, you need to eat it immediately, not mess around. But anyway, different conversation. The second issue, which I also mentioned before, is that PVDF, when it's stimulated, doesn't produce an enormous amount of charge. And normally, that might not seem like such a problem, but if we want to make an array or something big, what that means is that we only have a little bit of charge to work with and to overcome all of the parasitics, and there's lots of parasitics. We have parasitic capacitances, but in an array, we'll also have parasitic piezoelectric elements, which is really problematic. And so we need to figure out how to get around this. So what's my solution? My solution is to add transistors. And this is an old idea, but it's one which I think organic field effect transistors really enable. And basically, here on the left, I show a simple process where we make an organic field effect transistor. And it might look upside down, and that's normal for thin film transistors. But basically, we have a gate here on the bottom. We have a gate dielectric, source and drain semiconductor. And then, if you apply charge here, you can either accumulate or deplete the channel. And that can make a device. So that's one type of transistor. But in a kind of a parallel process with only one extra step, we can also make the transistor I show on the right. And you notice that that transistor doesn't have any gate. And instead, it's gated by the charge that we have in the PVDF. And so when we strain the PVDF, we get a charge here, and then the image charge that's formed on the channel then gates the transistor. And that has a number of significant advantages. It has much lower parasitic profile. It can also hold charge for a long time. And so by going through this flow, we can make switching transistors, and we can also make transistors that create what is effectively a charge amplifier for the piezoelectric material right there on the structure without having to route the charge, which then creates leakage and other challenges. If anyone's interested, we can get into the gory details of making the devices. There's lots to it, and we don't have to get that into it. But basically, the long and the short of it is, in order to get acoustic performance, we need to really squeeze all the knobs. We use 2 threshold voltages because we need a different threshold voltage in each transistor. And we also use a couple of strategies for backside alignment, et cetera. But this is kind of I'll say the maximum version of that system. So the very first system we made actually had 80 transistors, and it had 80 wires coming out. And I was shopping it around to try to get funding. Program manager was like, no, this is totally not going anywhere. He said, can you reduce the number of wires? I was like, of course we can, with more transistors. And so that's what we did, which was great. And so this has, it's fully matrixed. So it has 8 columns, 8 rows, and 1 common in the back. And half of the transistors are those switch transistors, and half are the sensing transistors in the structure. And that allows us now to localize the signal that we get. And the really key thing is that if we have a signal here and we need to measure it out here, we need to first ignore everything that's happening everywhere else along the line. And the switch allows us to do that. But the second thing that allows us to do it is we're not measuring charge on the far end. We're measuring a current. And if you guys remember the story of the transatlantic telegraph cable, I don't know if you covered that in your freshman class or anything. So translated telegraph cable initially was a charge measurement structure. So they drew the cable at great expense, and they tried to measure the voltage on one side, and they put a voltage on the other side. And they couldn't see voltage, and they just kept waiting, and they cranked up the voltage, they turned up, and they burnt the first cable. And so anyway, so they fired everybody, and they hired William Thomson. They drew another cable, and William Thomson said, no, the mistake is that you're trying to measure a voltage on the far side. He said, you need to measure a current. And he built a very clever ammeter using a mirror so that it created a long lever arm, and that worked because the current can overcome all the parasitic capacitance between the source and the end. So having a charge amplifier measuring a current instead of trying to measure a charge, which just dissipates along the capacitance and fades as a voltage on the far end, is, I think, quite strategic. Anyway, we're able to turn the knobs and get an acoustic performance, which is fine. And this is kind of an early, but I think powerful demonstrator of what it can do. So here what we've done is we take a stream of compressed air, it hits the surface, you can see where it hits, and you can also map the jets and watch it going around, and you can do all sorts of things and put it in an air tunnel, wind tunnel, and watch turbulence and see where the turbulence kicks in and things like that. You can also see sound. It's nice because it's big enough that you can, it's big enough to see the wavelength of sound, and you can measure it. And here I have two speakers that are synchronized, and so it creates an interference pattern, which is kind of fun. And you can scale it up. You can also scale it down. We have a collaboration in which we've taken this, and this is only a single element now. I'm trying to convince them to add a second element, which they're not convinced is useful, but because you can scale it. And what's nice is it has enough SNR, you can thread it inside the cochlea and use it as a pressure sensor. I mentioned before that it acts as a good hydrophone. But more recently, we've also shown that we can basically just use it in the strain mode and put it between the umbo and the round window. And then as the eardrum moves, that bends the lever. And so it also creates a charge, and that actually hopefully will have some application as an implantable microphone for cochlear implants. And then we've also worked on scaling it up a little bit. So we've licensed this to a company in Canada that makes surgical tools. And their tools have, it's like virtual reality for surgeons. It's kind of cool. And so the brain all kind of looks the same. And also most surgeries done through ports, so you also can't see anyway. And what their software does is they use these motion capture balls on the surgical tools. And so the surgeon looks up at a screen and they can see on the MRI or other imaging where they are. The problem is that the tools have a tendency to flex and move as well, and the models assume rigidity for the tools. And so we've made some compensation mechanisms for them that have both strain sensors as well as the piezoelectric sensors, and that offers some feedback. And we've also used it in some robotic fingers. And so we've used it, and we can talk about this later, for touch sensing, proximity sensing, and then I was very proud of this wired, but actually our finger was just the time invention of the year last year as well. So I should put that in instead to show off. But we use that together with some optical sensing, and then the piezoelectric sensor allows us to tell when the object's starting to slip because it makes like a little chattering noise, but it doesn't give an absolute force, and so we use the optical in this case, and we use a strain sensor in this case to figure that out. So there's lots of things that you can do with it, and once you have the system, then you can really start to play. So I mentioned organic field effect transistors, and one of the challenges with organic field effect transistors is that the mobility is not that high. Even though the thermal budget is very good, they don't push a lot of charge. And for microphone, you don't need a lot of charge. You just need to see when things are or are not happening. But there are other cases where you need a lot more oomph. And one of those is to make displays. And in particular, I'm very interested in micro-LED-based displays. And the idea behind micro-LEDs is to take what you might see at Times Square or in one of those LED monitors outside and to figure out how to shrink it down so that you can have an individual control of each pixel, but for a, I'll say, rationally sized display. And there are different applications for this. You can make micro displays. You can make sort of screen-sized displays. And there are a lot of advantages to using LEDs. LEDs are extremely efficient, they're extremely bright, and they have a very high power, peak power. That's nice. But there's a problem with them, which is that, and again, not to bore people too much with the math, LEDs in principle can be driven using a passive matrix. And if I don't know, you guys have like a bus transportation system, right? So like the signs for the bus transportation, they're like little LED boards. So what I always recommend to students that are curious is if you take your phone and you put in the slow-mo mode, take a look at that screen, and what you'll see is it runs line, 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 and then it cycles back. But if it has 10 lines, that means when it drives the first line, it has to drive it at 10 times the luminance. I think, Steve, you were the first person to point this out for OLEDs, so I'm not going to take credit for it. But you have to drive it at 10 times the luminance. And then the second line, you drive at 10 times luminance. But that whole time, the rest of the lines are just sitting idle. And if you do the math, the voltage drop across the interconnect scales with the number of lines cubed. A typical display is 2,000 lines. So I don't care how good your resistance is. Like, as a passive matrix, you're not going to drive any large size display. You really need an active matrix. And with an active matrix, that scaling changes dramatically. It's just the number of lines squared. And number of lines squared is actually a rational and doable thing. So how do we do it? So our approach is using an active matrix by adding transistors. You'll notice a theme here. So I drew this picture first. And this is almost what we wound up making. So you start with an LED wafer. I don't know how to make LED wafers. I wish we had epi growth at Columbia that could do LED wafers. That would be amazing, but I just buy them. They come off the streets. So we can process the LED wafers. What we do know how to do is make transistors, and then we add the transistors on top, and we put them together. Now, even though gallium nitride, when you grow the gallium nitride, that can be done at very high temperatures. You can't take LED wafers and heat them to infinitely high temperatures. The doping that's at the top layers, the contact doping, unfortunately doesn't withstand very high temperatures. So how do we then build transistors on top? So I want to make better transistors, and so the approach that we use is one that's called low temperature polysilicon, which again, I can't take credit for inventing. But the trick to it is that you can start with amorphous silicon, which can be deposited at low temperature. You melt it, you let it cool, and then it forms a polycrystalline structure. And Jersey, who's sitting in the audience, is one of the people who developed this in the good old days when it was first starting. And there's an important trick to it, which I think can be credited to your group, which is before you deposit the amorphous silicon, to put down a layer of something that can withstand high temperatures. So we normally use silicon dioxide. So you deposit silicon dioxide, you deposit amorphous silicon, that can all be done in one go. Then we hit it with a very short pulse laser. And that short pulse laser heats up the surface, melts the silicon, and then the silicon cools, and it forms this polycrystalline structure, which makes extremely good transistors. And my colleague James Im has shown that you can drag the crystal grains in a way to get almost, not quite, but almost single crystal type mobility without having to do any really advanced tricks. Now, you'll say, wait a second, you just told me this is a low temperature process and we're melting silicon. Silicon melts at 1500 C. So the trick here is I mentioned that it's a short pulse laser. So we use either an excimer laser, we have another system now that also gives a very short pulse, but is not an excimer. So unfortunately, xenon is not easily available anymore. I don't know if you guys are having trouble getting xenon, but that's like a big drama. But anyway, when you hit it with the pulse, it gets hot, it melts. When it melts, it sucks in the heat of fusion, kind of like an ice cube melting in your water. That cools the silicon slightly. It then solidifies, it pushes that heat of fusion back out, and it gets hot again, and then it relaxes. All that happens 0.1, 0.2 microseconds. So we hit a very high temperature, but the heat diffusing from the top to the bottom takes about 2 microseconds. And by the time that's happened, we've spread all of that energy across a thermal mass that's about 10 times that of the silicon we melted on top. So it's possible for us to make relatively high performance transistors without really damaging the substrate. And this is used commercially all the time. If you have an Apple Watch, any Samsung products, the displays that are there are made on something even more sensitive. They're made on a plastic sheet in which the silicon transistors have been processed that way. But it's nice because it allows us to put silicon on anything. We can also put it on LEDs. And we can use it to make an active matrix. And all of this is kind of the sort of the product of that happening. We've licensed this to a small company that makes some microdisplays and is working on trying to license them. And that works, I think, pretty smoothly. And what's really great about it is, again, we get the native properties of the LED. Oh, this is supposed to play Tetris, but it's not that exciting. But in a display, that's 1 million nits, or actually even more if you drive it just a little harder. You get maybe like 4 million. But it's nice. It's totally monolithic. And we get it thanks to the fact that we can latch and leave on each of the pixels while we're going through and switching all of the rest of the display. If we were trying to drive it one row at a time, it wouldn't happen. Now, unfortunately, I don't know how the rules are here in Michigan, but at Columbia, once you've licensed something out, you're supposed to stop working on it yourself. And I was starting to panic that I would have nothing to do. Okay, I see you shaking your head. So I guess you have the same rule. Oh, all right, we got to talk. Because then, you know, that sounds good. Well, we've been looking for other applications. So what can we do that's not going to compete with the company? And it's 12 PhDs, which, you know, I don't want to like throw like first-year PhD students up against the, you know, the high wall of competing with the startup. So, you know, in addition to using it for displays, I think there's a lot of other opportunity. And one of those is to use it for patterned and super resolution light sources. And so we've been working pretty extensively with a group in the University of Colorado. It's half the people are in Boulder, half of them are in Denver, but that's sort of neither here nor there. And what they do is they're part of this consortium that's really led by a group at UCLA, in which they make these mini scopes. There's microscopes that get implanted in the brain of the mice, and then the mice can run around. And the real key part of it is that the whole system has to weigh less than, depending on who you ask, 4 grams, maybe 3 grams. It's supposed to be 10% the weight of the mouse. 30 grams is a pretty small mouse. It's a pretty big mouse, actually, but that's a whole other discussion. And what you see people doing to get around this weight limit is like attaching a helium balloon and things. And it's like, okay, what we really need is better electronics, and that's something we can deliver. So the optics in the system are pretty, it's very clever, but the optics are really bad because they're very small. And so, you know, the group that we work with uses 2 different kinds of objectives. They use a Grin lens. They also have a really cool electrowetting lens that our collaborator makes. But all of it has lots of aberrations, and there's a lot of drama. And so what they would really like, and what we make for them, is a lightweight system that can shoot out patterned light. Because with patterned light, what you can do is shoot out different frames, snap pictures, and then reassemble those, and that can allow you to get higher resolution than is otherwise possible, but also allows you to cancel certain aberrations that are in the optical system. Now, they had previously demonstrated this with like a tabletop system, because you can do this with a DMD, but that then doesn't run around with the mouse. So the whole thing has to be, again, less than 4 grams. And so, of course, for us, the LED part is extremely light, and so that works pretty smoothly, and that's kind of one version. And then we also now have a dot version, which in principle can be used for optogenetic stimulation, but I will call you when they get it working. What we're able to do is get like it's a passive matrix. So it's everything I told you not to do, but we only need to drive 1 LED at a time. So 1 LED at a time, you can drive with an extremely high intensity. And that system just came together recently and has now been packaged to be implanted on the mouse. And I was just dealing with that earlier this week, which is nice. Now, this low temperature melting on the back end, I think, has a lot of other applications. So we had a program with IBM research looking at doing this on the back end of silicon. And you'd say, wait a second, we already have transistors in silicon. Yeah, we do, but there's been some effort to create back end of line integrated devices. And we can anticipate what most people would want, which is memory, but you can also imagine imagers and other things as well. And we've shown that you can, of course, do it on the back end, and we've shown that we can make wires, diodes, and more recently, gate-all-around transistors, which is nice, using the same general technique, which is, again, to shoot it very quickly on the back end. And it turns out that low-K is slightly better than traditional semiconductors. And yeah, so that's basically another kind of direction you can go. All right. So I've spoken a little bit now about using gallium nitride LEDs in inorganic. A lot of our work has been on flexible electronics and things that are bigger, which micro LEDs can sort of deliver. We'll talk about that in a minute. Another area that we've been really interested in is using light sources and sensing to map blood flow. And it turns out, even though blood flow might seem like it's pretty basic measure of health, there are a number of health conditions that can be diagnosed by understanding the blood flow and how the blood is oxygenated in the body. And perhaps one of the more, I'll say easier ones to understand, but harder ones to implement clinically is to use optics to map the focus of epileptic seizures. And so we have a great collaboration with Ted is a neurosurgeon, and Hung Tao is an MD PhD that works in his group. What they've shown is that the brain is very tightly vasoregulated. The brain uses about 20% of the energy of the body, but when you look at the brain, it looks white, which is weird, right? Like you would think there should be tons of blood in the brain, and there is. I mean, part of it why it's white is because of the myelin, but it's also because the blood flow is tightly regulated. It's only when you start using part of the brain that the blood vessels open up. And this is why functional MRI works. So the functional MRI can tell what you're thinking, because the parts of your brain where you're dreaming about cookies or thinking about revenge for your mother-in-law or whatever, that part of your brain, then the blood vessels open up and you can see more oxygen flowing there. And it turns out when you have an epileptic seizure, that region also has a greater blood flow. And Ted's group has demonstrated this primarily using animals and humans where the cranium is open. They get about an hour with each human subject before doing surgery in which they remove part of the brain. And they routinely get volunteers, which is kind of amazing. I know, yeah. Now, one of the reasons they get an hour, though, is that about 80% of people with epilepsy, drugs solve the problem. And about 20% surgery is really the main solution. Now, there are some other options like deep brain stimulation that have been shown to be effective, and that may actually one day eliminate the need for resection. But until that happens, the key thing is to know where to start. And the standard of care today is to put electrodes inside the brain, inside the skull. They're not in the brain, they're on the surface of the brain. You hang out for about 2 weeks in the hospital. You look at which line is the squiggliest, you pull the electrodes out, open up the skull, and then you start the surgery at the point where those electrodes are. But unfortunately, at the surface of the skull, the surface of the brain, the resolution of that survey is only about 1 centimeter. And that's why when you watch those really boring surgery movies, they plant the flags and then they move 1 millimeter at a time and it takes the whole day because they're not really sure where to go. And of course, you also want to make sure you're not cutting out a part of the brain the person needs. But the first thing is finding the focus, and they put a pin in, they stimulate the pin, they see if it gives a seizure, they move it 1 millimeter, and it can take the whole day. So they scrub in at 4 in the morning, and sometimes it takes more than a day. Optical response, on the other hand, has a resolution of better than 100 microns. So, if we can make it better than 1 centimeter, we can make things better. Now, in order to do this, though, we have to figure out a way to get under the skull. So, Ted called me up one day and asked, can you make me a flexible optical photodetector? I said, that was the subject of my postdoc. Of course I can. And we'll see that the answer should have been yes and no, but I said yes. And anyway, so we did a couple things, and not to bore people with the early work, this was our first dream, was to make an OLED and organic photodetector all in one go on the same substrate. And what's great is making organic light-emitting diodes and making organic photodetectors kind of like making a sandwich, where you make a P-type slice of bread, you make an N-type slice of bread, and then the filling is different, and you put the bread together. So, I'd say 80% of the process is the same, and it's really just the middle layers that were different. And then we did that on a polymer substrate, and we did some encapsulation, and you can make different colors, and you can do all kinds of things. And anyway, so all good. And we can make this very flexible. We can make it very thin, and it works. So these are some measurements directly from animal. And the animal was mechanically ventilated, which is a little bit cheating because you know exactly when the respiration is going to happen, but you can see the heartbeat a little bit, and then this big dip is that change in blood flow that's associated with the onset of the seizure. Now, anyone who works with OLEDs will tell you there's one enemy of OLEDs, which is water. Now, when you do this kind of survey and surgery, the whole thing is bathed in water. And try as we did, we just don't have a great encapsulation. So we need to learn how to do much better encapsulation without waveguiding. So we were able eventually to get a decent encapsulation by making a very thick multi-layer of parylene zinc oxide, parylene zinc oxide. But once it's too thick, the emitter and the detector just talk directly to each other and they ignore the brain. So a little bit problematic. But so even though in air it worked okay, underwater it would only work for 2 hours, 3 hours, which made our collaborators very upset because the animals were being sacrificed for this, and so we needed to change something. So I mentioned before our interest in micro LEDs, and in addition to using micro LEDs as a monolithic microdisplay, it's also possible to take LEDs, break them into chiplets, and here we had a collaboration at the time with Cree, which commercially makes LEDs. So for them, I think it was relatively easy. And so they make very small chips of the LEDs, and we can then process them and basically do the same thing, with the advantage that these survive indefinitely underwater. The only problem that I had, which is again kind of like only my problem, is we could get LEDs that were very small and place them and position them and all that, but I couldn't get any collaborators to do the same thing for my photodetectors. And until I realized, we don't need photodetectors. We have LEDs. LEDs are great photodetectors. And it turns out, even though the responsivity is not that good, the detectivity is excellent. Because if you use the blue LED as the emitter and the green LED as the detector, the dark noise for the green LED as a photodetector is 0, right? It has really, really no dark noise. So you get this is the LFP. Sorry, I haven't been talking to you through the graphs, but the LFP is the local field potential. This is like the electrical signal. This is the optical signal. And you can see when there's a seizure, the reflectivity drops, and then it recovers, and then it drops again. And this is for smaller seizures. And there are different poisons they put on the brain to make either baby seizures or big seizures. And that's something that you can then monitor and map out. Okay, so we did lots of kind of stuff like that. Okay, so we build this system, and to test it, we need brains. And I mean, I don't do brain surgery, and it's all right, it's kind of a limited market. What else can we do with it? So other collaborators have new ideas. So this is with Thomas Helscher, who was at Columbia, but recently moved to NYU to start biomedical engineering department there. And he's an expert in diffuse optical imaging. And the idea behind diffuse optical imaging is basically if you have a light source and a photodetector, if you've ever taken a flashlight and shown it through your finger, you can kind of sort of see your bones, but not really. And so the idea there is to use that same kind of diffuse sort of sensing, but if you have multiple LEDs ideally, or multiple lasers, and multiple photodetectors, a photodetector that's close by will see scattering that happens from a certain volume. A photodetector that's further away will see scattering that happens from a larger volume, and so on. And with multiple LEDs and multiple photodetectors, you can do some math and invert some approximate idea of what's happening, even in a diffuse solid that you might otherwise think gives you no information. So the student that was working on the brain probe, together with Andreas and also with a former postdoc of mine, took essentially the same structure and showed a couple of things. The first is that you can wrap it around the finger and do exactly what I described. And you can try to figure out how much space there is between the bones in your finger. And if you have arthritis, and there's some other diseases like lupus where the bones get closer together, you can now map how far the bones are and then map the progression of the arthritis with this band that's on your finger. We also have started collaboration with a university in Jordan to look at doing the same thing but in people's toes. And they're not looking specifically at the bones, but they're using the same diffuse optical imaging technique to look at the blood flow in one of the veins that's on one of the arteries, rather, that's in the toe, to see if surgery that tries to reconnect the circulation in the foot has worked. And here you can see, again, this is all in the paper in real detail, but this is what we saw in the pre-surgical case, where they put a blood pressure cuff and tightened the leg. And then in the post case, you see that the refill is faster in the post case. But normally you can't see this. This is just like a bulk measurement. Using the diffuse optical imaging, we can pick out the optical signal that's attributable to the vein, to the artery rather, that's in the center of the toe. And then more recently, we've been working on trying to take this system, which is on Andreas's lab. So this system does the same kind of diffuse optical imaging, but on the breast. So a patient comes in and flops into the system, and it basically flashes lights into different areas and then detects them using, it's actually pretty cool. It has a photomultiplier tube and an optical multiplexer, but also looks like a torture machine. One of my former postdocs is at FIT, which is our local fashion university, and they have an entire like bra lab, basically, where the students learn about women's garments. And so we've been working with them, and this is, we have a more beautiful version of it right now that was made for us by a company that's working on a new project with us. But basically, this one works fine as well. And so basically, it's the same strips, just on the breast. And this isn't going to detect breast cancer. But what it does do is, after surgery, it can map where the blood vessels are and look at the blood vessel healing post-surgery. And it's been shown that, particularly if you haven't removed the cancer, a cancer resurgence will recruit more blood vessels, so you get an uneven healing. And that's something that Andreas has shown he can map out. And so, instead of having it just at the torture chamber, hopefully you can have it in a doctor's office, or I don't know if you sent people home with it, what they would do with it, but at least in principle, that might be possible. And this is a series of experiments where they pinch off one of the arteries in the breast, and then they have people hold their breaths, and you look at the refill as a way to map out those blood vessels. How are we on time? All right, I'm going to talk about two more quick things. In addition to putting transistors on top, we can also put piezoelectrics on things. And I mentioned before PVDF and starting with the piezoelectric, but there are also many thin film piezoelectrics that have been developed. And I'm very jealous that your clean room has an aluminum nitride sputtering system. Wow, I wish we had one too. So we've been using a different piezoelectric, which is nowhere as good, but works fine. But what we've been trying to do with it, which I think is interesting, is we talked about touch before, but what about smell? Electronics normally don't smell. And one way to fix that problem is to set them up to detect mass. And in particular, the mass of what? Well, if you've ever taken a shower and the window or whatever, your mirror is cold, the vapor from the shower condenses on the mirror. And so that condensation tells you what vapors are in the space. I mean, what's a vapor? A vapor is a chemical that has a vapor pressure high enough to sometimes be a gas, but low enough to sometimes condense. And so, so if we can measure the attachment of vapors on the surface, perhaps we can detect how many vapors we have. Now, the problem is that attachment of vapors to a surface is pretty weak, and the vapors are also very light. The molecules are very light. So we need a scale that's extremely sensitive. And in the past, a lot of folks have used quartz crystal monitors. If anyone here has used them, if you've worked in the clean room, you know exactly what I'm talking about. And you've probably broken many of them. I know I have in my life. Quartz crystal monitors are basically a freestanding quartz crystal, and it creates a wave inside. And then as you add mass to it, that increases the inertia, et cetera. And quartz crystal monitor operates in the megahertz, maybe relatively low region. And they're reasonably sensitive. But it turns out that the sensitivity to mass accretion is proportional to the frequency squared. So the trick to really sensing things more sensitively is to push that frequency up. Now, I mentioned with the quartz crystal monitor, it's freestanding quartz crystal. And I mentioned the freestanding because it has to be thick enough to be strong enough to then stay in space, and it reflects that sound wave off of both sides. Now, the resonant frequency is given by the thickness. So the quarter wavelength kind of distance there determines what that resonant frequency is. So if we want to go to a higher frequency, we have to make it thinner. But if we make it thinner, again, you've already broken some quartz crystal monitors. We can't really go much thinner with a freestanding sheet. So what we need to do is instead put it on a mirror in most cases. And there are some new strategies that allow you to have suspended materials, but our approach has always been to use a mirror. And so what we can do is put down what is known as a Bragg grating, which is not that important, but we can start with a silicon wafer. We put all our circuitry down here. We then build a mirror. We put the piezoelectric crystal, and we can make this really thin to push the frequency up. And where, again, in quartz crystal monitor, you might operate in the, again, tens of megahertz, we're able to operate at 2.5 gigahertz, which really pushes up the sensitivity. Lots of processing and lots of cool things. I mean, the most important thing is that we do not need high temperature in order to get this nice crystalline texture, which is great, and there's some tricks to doing that. And our first, this was our first tape out. We fortunately got like the corner left over from some other project. So they gave us a huge amount of space. So we were like, how much space do you have? And they're like, so we made 24 of them, which was unnecessary. And this basically shows how it works. So this is a bare surface with us pushing some vapors in. In this case, we're using toluene. And then if we put a sensitizer, and we used a silicone, we used another polymer, basically that is like a sort of is able to grab on. And in the presence of a sensitizer, it can then get extra mass that slows down the resonant frequency. And then you can use that, in principle at least, to make kind of an electronic nose type system with different sensitizers, et cetera. Anyway, then we print them. There's some kung fu to making it cancel some common mode stuff. And we can see a lot of things. And then the real hunt now is for better sensitizers. So we have a collaboration with the Austrian Institute of Technology. They have a receptor, for example, for cyclohexanone, and we've shown that our approach is better than measuring it optically, which they had previously done, and it works pretty well, and it has the characteristics that they're looking for in the system, and we just keep making more of them, and I won't bore people with other parts because I want to show one last thing. So I mentioned a lot about sensors, but where can we go with actuators? And so this is a material that I'm really obsessed with. This is a polymer material, which is related to PVDF, but it's a terpolymer, and it has a very high dielectric constant. It has a dielectric constant close to 50. And so it's a really great electrostrictor. And when you apply a voltage, you can get almost 5% strain. Now, problem is, I say a voltage. The voltage is pretty significant voltage. So how do we control this at reasonable voltages? And I think you'll already know what the answer is, because my solution to all problems is to add transistors. So what we can do is we can build a level shifter. And Jay mentioned earlier that my PhD thesis was in field emission displays. It was actually in active matrix field emission displays. So I had to make these 2,000 volt transistors, thin film transistors, which was a nightmare. And I thought I was going to subject a student to the same nightmare until we realized, wait a second, this material has a dielectric constant of 50. Who needs a gate insulator when you have the substrate? And so you can build the level shifter right on it, use the substrate as the dielectric, relatively easy, couple transistors, good to go. And yeah, we've shown that too. And so that was kind of fun. Haven't totally figured out what to do with it yet. If you have any ideas, let me know, but we'll go there. Okay, so I hope I've convinced you, crystal electronics are great. I'm not here to tell you that we're gonna overthrow the silicon hegemony or anything. Silicon electronics remains a very important part of the whole ecosystem. You'll notice every single thing we made uses silicon electronics as well. But with thin film electronics, we can kind of add some extra functionality to things. And we have that low thermal budget. We don't need epitaxy. And in some cases, we have some mechanical properties that are also favorable. And I hope I've convinced you that with this approach, we can mix and match some of the functionalities that we need, especially when we use transistors to add either gain or selection to make new systems in the future. So I just need to thank the people that really do the work, my students, the folks that pay the bills, and just want to thank you very much for your attention.